So in this series of advanced data structures and algorithms, we are currently learning the topic of Fibonacci heaps, in which we have spent a couple of lectures previously, and we have looked into what actually a Fibonacci heap is. And then, as it is a data structure, and with any type of data structure, the most important thing is what all operations can be carried out on that particular or using that particular data structure. So we have looked into the operation, some of the operations as well. So our today's agenda is we will be diving into more details of other operations which are not covered as of now in case of Fibonacci heaps, and we will be also looking into their amortized analysis. And why specifically amortized analysis? Because when analyzed in the in amortized manner, Fibonacci heap gives us a lower time complexity for most of its operations. So let us quickly start with quick recap or a quick recall of what actually Fibonacci heaps is and what all we have completed till now. So Fibonacci heap data structure, when we talk about it, actually serves the dual purpose in the sense that first of all, it supports a set of operations that constitutes a mergeable heap. So it supports mergeable heap operations, we can say that simply. And secondly, these heap operations runs in constant amortized time, as I have told you. So what all operations we are talking about? So here is a list of operations which involves make heap, insert, minimum, then extract min, union, decrease key and delete. And among these operations, we have seen make heap operation, we have seen insert operation, we have also seen the minimum operation. So these three operations we have seen along with their amortized analysis, and that amortized analysis is done with the help of potential method, in which potential of one particular structure is being decided and then it is being worked upon. So these operations we have seen, and now we will be moving to the new operation which is about uniting two Fibonacci heaps. So when we want to unite two Fibonacci heaps, let us say they are H1 and H2, we need to unite them, but the important thing which is to be taken care of is we need to destroy H1 and H2 which are existing in a separate manner, because we are looking for an union of H1 and H2. So this basically in order to unite H1 and H2 to Fibonacci heaps, we simply concatenate the root list of H1 and H2 and determines the new minimum node. And afterwards, as I told you, that the objects representing H1 and H2 they are to be destroyed and they will be never used again. So here is a small pseudo code of how to how to unite H1 and H2. So the procedure is named as fib heap union. The two objects H1 and H2 which are separate Fibonacci heaps are being passed on to it, and it is very clear that we need to unite them, we need to make a union of H1 and H2. So here we have created one H, which is created or we can say with the help of make fib heap procedure or create heap procedure, that is to create an empty Fibonacci heap. And now the minimum of this H, the new Fibonacci heap is being assigned as the minimum of H1. Then the concatenation of the root list of H2 with the root list of H is being done, because when we say H dot min is equals to H1 dot min, that means we have given our this H1 object onto this H thing. And now if H1 dot min is equals to nil, that means or H2 dot min not equals to nil, that means this H1 dot min nil. Here if we are comparing, that means we are trying to look into the existence of H1, if it really exists or it is a kind of an empty heap. Or we can say if this is not nil or H2 dot min not equals to nil and h2 dot min dot key is less than h1 dot min dot key. That means your h1 is not nil, that there is an existing Fibonacci heap h1, and similarly the second one, which is the h2, is not nil, and also the key of h2, the minimum key of h2 is less than the minimum key of h1. That means among this h1 and h2, the minimum is the key of h2. So then in that situation, h dot min is equals to h2 dot min. That means the minimum key of h2 will be assigned as the minimum key of h. So whatever whichever is minimum, h1 or h2, that key will be assigned to the minimum key of h. And then after all, as we have concatenated these two root lists, the number of elements or number of nodes in h1 and h2 are to be kind of, we can say, added together in order to determine the number of nodes in the new heap or in the united heap h. And for this we can say h dot n is equals to h1 dot n plus h2 dot n, and finally we need to return that object which is the new union object h1, which is the union of h1 and h2, and that is return h. So this was basically we can say an algorithm that how to go about the uniting two heaps. Now let us say we take an example, but before going into example we also need to look into the analysis of this thing. And as I have told you that we are going to take amortized analysis for the analysis of Fibonacci heap operations, and within the amortized analysis the method which we have started with the other functions of or other operations of Fibonacci heap is potential method. So here also we are going to take potential method, and please recall that the potential for Fibonacci heap is number of trees in that Fibonacci heap plus 2 into the marked nodes, which is nothing but T of h plus 2 into marked nodes of h. So now here we have phi of h minus within the bracket phi of h1 plus phi of h2. So the change in potential which we are going to calculate is, now the new potential is we have phi of h, and now what potential we are missing out in the sense that those two heaps we have kind of destroyed or deleted, we can say. So that potential is to be subtracted from the newly added one. So that is why phi of h minus phi of h1 plus phi of h2 within the bracket. So phi of h here is going to be T of h plus 2mh minus within the bracket the potential for the first one, that is a heap h1, that is T of h1 plus 2mh1 plus the potential for the second one, which is T of h2 plus 2mh2. Now please take a look carefully that we have not changed in uniting procedure, we have not changed any of we can say the marked nodes, because they were not involved in they were not explicitly involved in uniting the two Fibonacci heaps. So no change in terms of marked nodes. And also the other component of the potential is T of h. So T of h is number of trees in h. So number of trees, let us say there were 2 trees in h1 and let us say there were 4 trees in h2, and then we are going to unite them, we are going to get 2 plus 4, which is 6 trees in the new Fibonacci heap, which is union of h1 and h2. So essentially if we can say T of h is actually equals to the sum of T of h1 and T of h2, and also there is no change in number of marked nodes. So 2mh is actually going to be equals to 2mh1 plus 2mh2. So essentially what I am trying to say here is there is no change in potential, because trees in h is equals to the number of trees in h1 plus number of trees in h2, and also m of h is equals to m of h1 plus m of h2. So amortized cost of fib heap union is equals to its actual cost, which is order 1, and also here is kind of we can say there is no change in potential in the operation of this uniting the Fibonacci heaps. Now, when we actually unite these two or any two Fibonacci heaps, we concatenate the roots of both the heaps, then update the min by selecting a min key from the new root list, and then finally we get the union of two heaps. This is where actually we can say a step by step procedure. Now, here let us take an example. Here we have two heaps. One is having two elements, only one is 17 and 30, only one tree is there, and the min element is obviously 17, and the next one is having some of the nodes in it, although the tree is in this Fibonacci heap also, the second Fibonacci heap also, the tree is having only there is only one tree which is rooted at node 24. So, 24 is there, then 26 and 46 and 35, and please notice that this 26 is actually a marked node in among these H1 and H2, and when we are going to perform a union, we are going to unite these root list in order to make a new root list. So, the new root list is having 17 and 24 as the element. With 17 there is a child 30, with 24 we have 26 and 46, and with 26 we have 35 also. So, this is what actually the structure will be after uniting the two heaps, and the new minimum obviously is going to be 17, which is the least among all the minimums, or here we have only two options, which is 17 and 24. So, the new minimum is 17, and also marked nodes are not changed in any case. So, no change in marked nodes. Actual cost of operation, if we see, is actually order 1, because we are just kind of concatenating two doubly linked lists, we can say. So, the concatenating the root list is not going to change the total number of items in the root list or the total number of marked nodes. So, the amortized cost, we can say, is actuals to the amortized cost is equals to the actual cost plus change in potential. That is the formula which is written on the the last line of your slide, as you can see. So, the amortized cost C hat is equals to the actual cost, which is order 1, and that that is the cost which is incurring which is incurred in uniting, or we can say concatenating the two doubly linked lists, circular doubly linked list, and then there is change in potential, and as we have seen that there is no change in potential. So, the amortized cost is going to be order 1, which is actually equals to the actual cost of this operation. So, we have seen a very small example of we can say how are we going to unite the two heaps, and how it is not going to it is not going to, we can say, trigger any change in amortized cost, and the amortized cost is equals to the actual cost, because there is no change in potential. So, this was actually the operation of uniting two heaps and its amortized analysis. Moving further, in our previous lectures we have seen that we have displayed the minimum, in which we have not extracted the minimum but just displayed it. Now, the next operation which comes up in the list is about extract min. We can say that it is one of the most important operations on a Fibonacci heap, because a hell lot of readjustment is required when we talk about when we remove the node with the minimum value, a lot of readjustment is required. So, extract min involves all that readjustment, and hence we can call that, yes, it is one of the most important operations on a Fibonacci heap. So, how are we going to execute this extract min? As you all are aware that we have a pointer towards the min node, we simply need to delete that min node and set the min pointer to the next node or to the next root in the root list, that next root may not be, or in most of the cases it is not the next minimum. Now some kind of, we can say, consolidation is to be there. So we need to create an array of size equals to the maximum degree of trees in the heap before deletion. Now what is the degree? Degree is actually the kind of, we can say, number of nodes in a heap root list, we can say. So we will be deleting the minimum node, setting the minimum pointer to the next available root in the root list, and create an array of size equals to the maximum degree of the trees in the heap before deletion. And then we will be doing some steps in a repetitive manner till there are no multiple roots with the same degree, because multiple roots with the same degree is here are we can say we need to avoid them. So in order to ensure that there are no multiple roots with the same degree, we need to follow some steps, that is to map the degree of the current root, which is kind of a min pointer, to the degree in the array, and then map the degree of the next root to the degree in array. So basically it is kind of a we can say consolidation work, and if there are more than two mappings for the same degree, then we need to apply union operation to those roots such that the min heap property is to be maintained, and we need to keep minimum at the root. So in short, we can say when we are extracting the minimum, we will be deleting the minimum node, then we will be creating an array for mapping of different different trees of different degrees onto that array, and then we will be mapping the degree of the current root to the degree in the array, and also the degree of not only of the root but also of the next root to the degree in array. So that mapping has to be done, and we need to ensure that there are no multiple roots with the same degree. Now let us see this with the help of an example. Here we have on screen, as you can see, we have an example which is having some we can say trees which are 23, 7, 21, then there is a tree rooted at 3 and 17 and 24, and minimum is pointing towards this value 3. And please notice the number of mark nodes or the situation of mark nodes. We have 18, we have 39, and we have 26 as the mark nodes. Now the idea is, or the agenda is, to delete the minimum node. So if we are going to delete the minimum node 3, so here we have the maximum degree here is 3. So the array which we are going to create will be of total 4 elements starting from 0 to 3. So if we are going to delete 3, all the children which are related to this node 3, which are the trees rooted at 18, the tree rooted at 52, and the tree rooted at 38, are to be combined to, or are to be kind of hanged on onto the root list, and then a consolidation is to be done. Let us see how. So if we are going to delete the mid node, we are going to add all its children to the nodes to the root list and set the min pointer to the next root in the root list. So we have deleted 3, we have taken its 3 children, which are the trees rooted at 18, 52 and 38. We have added them to the root list, and after that the next point is set the minimum pointer to the next root in the root list. So that is kind of, we can say, now it is pointing towards 17, although that is not the actual min. We will be finding the actual min in the after this consolidation step. But here, as you can see, now we have 23, 7 and 21 for degree 0 as well as 52 also, then 18 is for degree we can say 1, 38 is for degree 1, 17 also is for degree 1, and 24 we have for degree 2. But in the earlier situation, what was the maximum degree? If you can see, the maximum degree was 3. So here we are going to create an array of size 4, and now we want to map the degree of the next roots with the array. So, for example, the index here in the array is representing the degree of the node. So, 0 basically is pointing towards 23 because that is the first tree with 0 degree. That is not only, that is that is not the only tree, we are going to consolidate it soon. So, this is pointing towards 23, then the one the cell of the index number 1 is pointing towards the root which is the tree which is rooted at 17, and for the cell indexed at 2 is being pointed on kind of this tree rooted at 24, but consolidation is not being done. So, what kind of consolidation I am talking about? Let us see that. So, here if you can see 23 and 7, they have the same degrees, we need to unite them, and 23 as it is a bigger term will be because because we need to follow the min heap structure. 23 is going to be the child, 7 is going to be the parent. So, 23 and 7 we have united them. Then after that, now we have 3 trees of degree 1 which are 7, 18 and 38, 2 and 17 also, and then for 0 we have 21 and 52. Now, let us see what is going to be our next step. So, as a part of next step, we can see that 7 and 17 have the same degrees. So, 17 is having degree 1, only one child which is 30, same with 7. So, we need to kind of unite them. How are we going to unite them? Let us see. So, 17 as it is kind of greater than 7, as far as min heap properties are concerned, it is going to kind of take the position of the children of 7. And now the new structure, if you can see, is here which is shown on the screen. So, 7 with its 2 children 17 and 23, 21 with 0 children, 18 with 1 children, 52 with children 0, 38 with only 1, and 24 with 2 children. Now, here if you can see, there are 2 nodes which are having 0 degree, 21 and 52, 2 nodes or 2 trees with degree 1 which are 18 and 38, and then 2 nodes with degree 2 which are 7 and which are the trees rooted at 7 and 24. As a next step, 7 and 24, as I have told you, have the same degree. So, we want to unite them. So, this 24 is going to become the third child of the tree rooted at 7, and this is what has exactly happened. If you can see in this figure, so 7, then one child is 24, all a complete tree rooted at 24, then we have 17, and then we have 23. Still we are left with 2 trees of degree 0 and 2 trees of degree 1, we can say. Now, next, what is going to be the next step? We need to map these nodes as well. So, for 1 we have 2 which is 18 and 39, and for 0 we have 21. For 3 we have only 1 which is the newly united heap, which is the tree or which is the newly united tree which is available or rooted at 7 and having its 3 children. So, in order to map the next nodes, 52 and 21, as you can see, is having the same degree. So, we are going to unite them. When united, 52 and 21 will take part as the parent because of being minimum, then 52 is there. Now, we have 3 trees, 21, 18 and 38 with the same degree. Now, how are we going to proceed? We are again going to merge these kind of same trees with the same degree. So, here we are uniting 21 and 18. So, 21 and 18 when we have united, so 21 has taken the position of child of 18, and now if you can see, all the trees here are having different degree. The tree which is rooted at 31 is having only 41 as its children, then 18 is having only 2 children, which is 21 and 39, and 7 is having 3, and they all are, we can say, kind of mapped accordingly. So when mapped, the cell which is having index as 1 will point towards 38, or the tree rooted at 38. The one which is having 2 is pointing towards 18, and the one which is having 3 as its index pointing towards 7. And we need to map these nodes, and here we are going to have the final mapping as shown on the screen. So we have 1, 2 and 3. We do not have any kind of we can say any tree which is having 0 children, so that cell is not pointing towards anything, and the final heap, as you can see, as this is going to be the final heap. So one node, or one tree with degree 1, one tree with degree 2, and one tree with degree 3, and finally 7 is regarded as the minimum node, because this is having the lowest key among all availables in the root list. So this was actually we can say one procedure through which we are going to unite the heaps, and finally we are going to kind of map them after proper mixing and after proper coordination. That means there cannot be the 2 trees with the same degree if we are in the process of uniting them. So one tree of particular degree in a Fibonacci heap is going to be the final call, and here we have seen this with the help of one example, and final heap is here. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed one. From here onwards we will be moving into other details of potential functions, potential function calculation, and other operations of Fibonacci heap, but that too will be taken in the next lecture. I hope you have enjoyed this lecture. Thank you for a patient hearing.